I'm happy to welcome Markus Rabe from UC Berkeley here today to give us a talk about program synthesis and quantified elimination and QBF and things like that. So Markus has been there for a couple of years and did his thesis in Saarland University with Bernd Finkbeiner on hyper LTL. So I'm happy to have you here, and so just not to take away more time, please.
Thanks for the introduction. Yeah, right. My background is more in information flow security, form methods, temporal logics, and so on. But recently, I've been then more like shifting over to the synthesis aspect of formal methods mostly. And my overall goal is to apply this back into security. I think it would have a tremendous use. So while earlier, previously, or some years back, we still thought that critical programming errors result in things like that or this. Today it looks more like that. These are like scams, like that lock your computer and you can only unlock them for money, or like that where someone hacks into your car and you end up crashing your car. So I think there is a shift in the attention from the safety aspects to the security aspects, and that is, I guess, mostly driven by the economic impact, which is estimated in the many billions. I mean, these are obviously people who are profiting from a high estimate here, but I think it's fair to say there is a really big economic push towards it. I think today might even be the tipping point for like people taking security more serious, because today I think it was the first CEO who had to step down because of a big data breach. So that might actually change something. I don't know.
It's not the last one.
He's not the first one, really?
I don't think so.
At least of a major company, as far as I recall. Maybe there are more.
Security is the number one reason why CEO are fired today.
Okay.
I heard that quote.
Okay. I mean, they're definitely concerned about it now. Yeah.
Makes your point stronger. Maybe the tipping point has happened and we care even more.
Well, once we hear the Springfield stuff, I heard this quote several times.
Okay.
Anyway,
cool.
Go ahead.
So all the while, we actually know how to design secure systems, right? Like there have been several major attempts at formally verifying systems with a very high standard of certainty. The SEL microkernel was maybe the first really big example that shown that, but there are major other efforts in this area. However, of course, they still didn't reach practical or the normal software development, because it's still pretty expensive, right? So, and I think that for the cost reason and for others, I think that program synthesis will have a major impact, and I think that will be mostly in three different ways. First of all, the standard view of program synthesis is that we can synthesize performant code or low-level code from higher levels of abstraction, and that would reduce the complexity in software designs, or could help to. And in particular, it could reduce the amount of low-level coding that's really error-prone. Now, that is the sort of standard view of program synthesis, but I think there are different ways how program synthesis could be really used. You could also synthesize proof objects for theorem provers, which is, I think, would help to directly lower the cost of these major verification efforts. And we could also use that in automated program analysis in all its variants, and synthesize things like invariants, ranking functions, and so on. And by that, at least find vulnerabilities in existing code, which is also a very helpful tool, of course. Now, I see that, I consider program synthesis in a very general fashion here. I think that it typically has this pattern where we ask, well, does there exist some program or some syntactic object of some class of things that we describe, such that for all inputs, some specification holds. Typically, we can compile these synthesis problems into such a format. And that could be also does there exist a proof such that for all possible sums of the variables it is true, so that would kind of represent the theorem proving aspect of it, maybe. But I think if we manage to solve these problems in a fairly general and fast way, this could help in many different ways and would really help for software security. So However, of course, I think everyone is aware of that. Program synthesis is really not scalable so far. Like, if we are really lucky, it scales to 5 to 10 lines of code. But for that, we probably already have to restrict the problem very much. So this is really the biggest issue of that approach yet. So the approach that I want to take is to identify the fundamental scalability issues behind this. And for that, I want to reduce the problem to its simplest form, to a very like pure form where like you can actually analyze the problems. And that is, I believe, the simplest synthesis problem is quantified Boolean formulas. We'll even further restrict it to just quantified Boolean formulas with one quantifier alternation, just to look at the core of the problem, and that we'll study today. And for that, I will, in this talk, suggest a new algorithm, and then we'll evaluate it. And for that, we started out with some synthesis benchmarks that were essentially, well, synthesizing some proof objects first, and then we also took some benchmarks from the Sketch benchmark library, like that is Amando's. Amando helped us generating basically Boolean encodings of his program synthesis benchmarks. Well, the reason why we picked that is, well, obviously these were available. We didn't have to do it ourselves, which is, I think, a good thing for benchmarking, because that means you cannot cheat. We had the files first before we developed the algorithm. And then all these three families included some unsolved problems. And so it was possible to measure some progress towards synthesis there. Because I don't believe that we can suddenly scale to hundreds of lines of code. So we didn't want to set a goal that was too large. Now, just to be a bit more concrete, the ranking function problem has problems like that. We are given the Boolean program over some state variables. And we basically just ask whether there exists a constant c such that for all states x and x prime, if they are successors, so if x prime is a successor of x, then the multiplication of the constant with the state vector must be smaller than the the product of the constant with the previous state. Right? So a very simple encoding. That was done by Cook and some others. And they included problems mostly taken from Windows device drivers, of course very reduced ones, but they had realistic bit width. So they have their encodings of 16-bit, 32-bit, and 64-bit, and they all they have small snippets like that. I think this is one of the smallest snippets. It basically asks whether we've been given two variables. We only know about them that they are equal on their last 5 bits, apparently, for whatever reason, or they're not equal on the last 5 bits, sorry. And then we're counting the one up, and so apparently someone had a small counter in the last 5 bits encoded and tried to have a loop over these. Okay, it turns out this is a non-terminating program, because if index is different to head on a on the bits that it doesn't compare it with, then we store that in the integer I, and here in this comparison, it will always fail, because we can always count up the last 5 bits, but it will never do anything. So it's sort of as a human, you can spot that. It's not that hard, but it's not so easy if you just see a sea of clauses and bits. And this is a problem that can be encoded apparently in some 3,000 clauses with a 32-bit semantics. Has some 128 variables, so you don't want to enumerate things. And yeah, so in the end, it turns out we can solve these kind of things very, very quickly within, say, 100 milliseconds. Okay. All right.
So,
yeah, sure.
So, are you saying no ranking function exists, or opposite?
They exist, so there exists no ranking function, yeah. And to prove the absence is non-trivial. It is, of course, not particularly hard for humans, but we want to automate these things. And this kind of, I just want to justify, oops, that this is a reasonable benchmark for synthesis.
No ranking function exists means there is, it does not terminate.
Yeah.
Okay.
Yeah, exactly. And the other problems we considered were then things like function summaries of Boolean programs, and program sketches, and these were sometimes substantially larger. So the synthesis problems we considered were typically like 50,000 clauses, sometimes some had 100,000, 200,000 clauses. But I mean, this is not particularly impressive for SMT solvers or for SAT solvers, but we're trying to solve a harder problem here. So that's kind of, I think it's a reasonable synthesis benchmark. If we can do that, we did some progress. Okay. This talk will I'll basically go through this schedule here. First, we will take a look at the existing synthesis algorithms on the program level and try to identify what their problems are, at least one problem. I mean, I'm not suggesting here I'm solving everything. And then we'll do the step to QBF encodings. We'll take a look at that and see what the problems with QBF algorithms are. And then we'll go into the algorithm. We'll go through the evaluation. And then we have two parts that are kind of more in Outlook. There's one theoretical work on how to lift this to reasoning about functions and some quantitative works that also really neat. I hope we actually make it through the last part as well. Will depend a bit on the timing. All right, SIGIS. This is a very general algorithmic scheme to solve synthesis queries. Basically, we want to just have a very simple loop where we pick a candidate program, we want to check whether it's the one we're looking for, and if not, then we exclude some programs from the next query and iterate. Well, you can see that as a learning framework. People have been exploring the theory around that, and where, anyways, and there are two main flavors of that, which is the enumerative synthesis approach and the SMT solver approach. Maybe there's also the stochastic one that I won't go into too much today. And they both come with their problems. Like the enumerative approach is to enumerate syntactic expressions from small to large and kind of to always evaluate them against the counterexamples you have found so far. And that is, you can enumerate things really quickly, but of course it's clear that once programs get, like the problems we're looking for get too large, then the number of possibilities just explodes and we won't get anywhere unless we restrict the grammar so much that that number of possibilities is kind of small, but then we have to sort of know what we're looking for. So it's kind of not really a solution in the long run, I believe. So the other problem is to use an SMT solver, which does not necessarily suffer so much from this combinatorial explosion, but it turns out in practice it does. Like after we add some queries, I mean, SMT solvers tend to have really problems, at least on the Eve encodings. I'm not sure whether there are much better ones, but so far in literature it seems that often the problem is with SMT solvers that after adding a number of counterexamples, things really start to get slow. And there is one problem that both of these approaches share, which is that for some examples, you just need too many counterexamples. In particular for those where we have to refute the existence of an object in a certain grammar. Let's take a look at this very simple program sketch. I sort of think many people have seen that. Armando Soledad-Zama has promoted that kind of thing a lot. This is a program snippet or a small function that just has one hole in it, which is denoted by these two question marks. And the problem is to find a constant to insert in the by which you want to replace these two question marks, such that the program doesn't violate its assertion. Now, this function is really supposed to do something really stupid, really simple, just supposed to return a number that is different to its input, right? So we're given some y as an input, and we have to then choose a constant, but that is a constant. It cannot depend on y. And then they are supposed to be different. It's clear that such a constant cannot exist, right? Like for any constant we choose, you can pick the same input and it's the same, right? But SIGIS engines really have problems with this this example. They will just enumerate counterexamples, and each counterexample only excludes a single constant. So that's really that is a really awkward example for SIGIS. Right? Now, the way we're going to encode that in QBF is that we unfortunately have to negate it. This is a bit of a weird point at this point of the talk, but I assure you this is only for technical reasons because we want to work with CNF. So if we want to encode our constraints in CNF, there must be an external quantifier inside. I assure you this is one of the only points where this is a really technical, weird argument in this talk. So we negate our problem. Instead of asking whether there exists a program that works for all inputs, we're going to ask the question whether for all programs there exists a counterexample. It's just a negation of the problem. And then it's clear that our problem from above could be encoded in QBF like that. We ask whether for all x's there exists a y such that x equals y holds. I'm sort of assuming an optimal encoding of this program. Obviously, when we work with real encodings of programs, there will be a lot more clutter around this, but it's sort of clear that this is the core of the problem. All right. If we find a Boolean function for that QBF, that means we prove that QBF to be true, we have refuted the original problem. Then for every x, we found a y that satisfies this equation, which would then violate the assertion. All right. All right. Now, how do QBF algorithms solve that? And for QBF, so far, or at least until recently, the predominant algorithmic approach was the Seeger approach, which for 2QBF can be stated really simple. We just take two SAT solvers, one for the universal variables, one for the existential variables, and we first ask the one for the universal variables whether there exists an assignment to x. It gives us some assignment, where it has so far no constraints. We find then a matching assignment for y, which is an assignment that for that particular x satisfies the formula. And then we exclude all the x's, like all the universal assignments that for which this y is a solution. In this particular example we had on the previous slide, the equality constraints, this is exactly one universal assignment, right? And so, oops. First of all, this is basically the same as Sieger's, just formulated in the other way around, sort of in the negated form. And for our example on the previous slide, it's clear that we just exclude one assignment, and that leads to enumerating all assignments, also in SAT. And it turns out that even the competitive QBF solvers from the last couple of years that are based on this principle just diverge in that example. They practically never come back if you have to enumerate 2 to the 32 assignments. That said, this is only true if you don't consider preprocessing. There are preprocessors that can solve that, but we don't want to rely too much on preprocessing here. As soon as something like that equation hits our solvers, they're done. So it's the problem we see with Sieger's for synthesis tools does exist in the same way for QBF. So this is sort of another justification why it makes sense to actually study the problem in this low level, because we really have to solve this quantified problem to make progress. Now I want to take a step and just say, let's do something completely new. Let's take a completely fresh view on this, and consider so assume we're given a 2QBF for all x exists on y, such that the formula phi holds, and let's consider that as a relation between assignments to x and assignments to y, right? Like the relation, any pair of assignment to x and y either is satisfied by the phi or not. And this gives us a relation, implicitly defined, or symbolically defined. Yeah. Now we have, and what we want to have in the end is a Boolean function, which is nothing but a functional and complete relation. Right? So we sort of talk already about the same kind of object. It just needs some additional properties. We need to we need in the end to refute or to prove such a formula. We need to find a relation that is just has these additional properties. Right? So let's take this general relation view and look at what the Seeger algorithm is doing. So this the assignment, the relation here is basically a set of arrows between assignments to x and assignments to y. And now there are two cases that could make a relation not complete or not functional. Right? Like either there is an assignment to x that doesn't have a matching assignment on the other side, and this is sort of the assignment that all the Seeger algorithms are looking for. They kind of browse through the assignments here and always try to find something on the other side that matches it, and if they find something that doesn't have a matching partner, they're done. They found the counterexample, and at some point they otherwise exhaust the space of assignments to the universals, and they're done. Right? Now, we're going to now focus on the other case, namely the one that the relation might not be functional.
Excuse me a second.
Yeah, sure.
So to get a proof, it only has to be total, it doesn't have to be functional. Right? Now, a non-functional proof is overkill, so to speak. It gives more than one example that refutes every program. But nonetheless, you don't require to have a proof that this relation be functional. It's sufficient, but not necessary.
True. We could also prove it with non-functional. That's a good point. Yeah, we could prove it with non-functionals as well. The typical view how we want to prove it, however, is that's Boolean function, right? And a Boolean function is a functional thing, which is a function, right?
It narrows down the things you have
true.
to search.
True. That is also a good point. The point, however, why we want to have the functionality is that with that property, we can kind of turn this problem around and check for the completeness. Like if we have a functional relation, we can turn the problem around and check for the completeness of the relation with the set solver. Because then we can kind of ask, whether is there an input to that relation that creates a conflict? And that will help to, yeah. But I agree, yeah, we could also try to not generate Boolean functions, but relations.
Functions are sufficient. Right.
But or efficient, they constrain they constrain the X player. Functions constrain.
Yeah.
Making it a function constrains the teacher, right? It says that, so to speak, in the teacher learner.
Yep. All right, we're going to exploit that functionality, however, and this is, I mean, it comes really handy that it's typically formulated as Boolean functions and not by relations. Okay, now what we're going to do is to take our general relation and add new constraints until it becomes functional. So we want to kind of collapse these pairs where it's not clear where to go, like what the matching partner is. And on the way, we'll check whether we kind of violated that completeness constraint. Now, the question, of course, is what constraints to add. And here we're going to take a CDCL style approach. We're going to add simple things that are not necessarily correct. We're going to propagate and check whether we did mistakes, and if so, then we learn from that. We'll actually learn clauses, like in CDCL. Now, I think it can be best understood along this example. It's CNF. I'm aware that people are not fluent in CNF necessarily, but I'm going to lead you through it, and it's going to be really simple. So we have two universal variables, x1 and x2, and four existentials. Let's, for now, zoom in on the first three classes. These three classes all have a particular property. There's just one existential variable in there. The others are universals. So we can read them as implications, right? We can negate the left side and read them as implications. Now, then it's clear that these three classes describe three sort of function cases, or cases of a function. And it says, like, if both universals are true, then y has to be true, and otherwise it has to be false, right? So this is an AND. Right? This is basically an AND. And I'm drawing this circuit here on the right side just for illustration purposes, just what the current state of the function is that we learned. Right? So here we just learned, okay, this one variable has a, if this whole problem has a Boolean function, then this variable necessarily has to be the AND of these two universals. Now, we can do the same thing with the second group of variables. However, now, now we have these classes where there are two existentials. However, for the existential y1, we already know its Boolean function. So it's sort of okay to replace it by its Boolean function and just let y2 depend on the outcome of the Boolean function of y1. So we can learn here, okay, this is just the OR of x2 and the outcome of the Boolean function of y1. Right? So this is a propagation step that happened. By learning that y1 has a particular Boolean function, this enabled us to learn that y2 must have another Boolean function. And we could only do that by like after learning the Boolean function for y1, because otherwise we would have these clauses y1 or y2 that don't have a particular direction to them, right? Now, assume we have some more clauses. We might not always be lucky to derive all the Boolean functions. And these two clauses here for y3, they also have that property that y1 and y2 they have Boolean functions, and there's only y3 in there that doesn't have a schooling function. But these two clauses, they don't necessarily determine y3 for all possible signs, right? I mean, it's not functional at this point, right? So let's just add a clause, just decide for something. We'll later take a look at what exactly we want to, how decisions should look like. In this case, just add a single clause that says, like, if y1 and y2, so if these two clauses are satisfied by y1 and y2, that is, if they both are true, then y3 should be true. All right. Now, this together defines an AND. That's fine. We just guessed it. So we mark it blue, so this depends on the decision. Now we try to continue propagating. Look at y4, and we find out, oh, that leads to a conflict. A conflict is that we find an assignment for x1 and x2 for the universal variables that propagates through. So y1, x1, x2, insert them here. We get y1. Y1 implies y2. So y1 and y2 imply y3. And now we have this conflict that says if y1 is true, then y4 has to be true. If y3 is true, then y4 has to be true. And y4 has to be false. And y4 cannot be true and false at the same time, so we have a conflict. Right? Now, we have to find this with a set check. But we can, well, yeah, we have to find this universal assignment with the set check, maybe, but that's fine. And now we can go back. We do conflict analysis like in a SAT solver. We learn a new clause, like this. Now, it actually turns out that now if y1 is false, then y3 has to be false. And if y1 is true, then y3 has to be false too. So basically it means like y3 is defined to be constantly false here. That's fine. We learned that through the conflict clause. We can propagate that, and it turns out this works. So like then we can just complete that other thing. That's fine. So what we did is now we learned a schooling function that has 3 distinct inputs. But we only needed one particular, we only needed one subject to find this one conflict. So some magic happened. A CGAR approach would have taken at least 3 set calls, so like 3 iterations. And in general, that there could have been like much more stuff around it that we just derived, and that wouldn't have taken any additional set calls. So really did something new here, I think. And I would say that this algorithm exploits the functional dependencies among the variables that are there in the CNF to define the schooling functions that are uniquely there, and thereby we avoid the enumeration of the inputs. So what I think this,
So you depend on the topological source.
The topology, or so the ordering among the variables, is derived on the fly. It's like there's no predetermined order. Is that a question, or does it answer the question? So while
What if all y's appear in all clauses?
then we're pretty much screwed. That usually doesn't happen though. Most of the, like in particular for like Zeitin encoded problems, clauses typically have 2 or 3 variables, or 4 or 5 sometimes. And like, okay. Okay, so I think the best way to see this algorithm is that we lifted the CDCL algorithm from SAT to the function space. Instead of propagating values, we're propagating functions. Or rather, we're propagating the property that certain variables have unique functions. But so this slide also sort of shows how this should be probably implemented. The state of a SAT solver is essentially a partial assignment of the variables, a mapping from variables to Boolean values or to an undefined value. In QBF, so in the QBF algorithm, we will have a partial assignment from existential variables, only the existentials, to either a schooling function or an undefined value. And a schooling function will just be described by a set of constraints. We won't have to represent them in any other way that they are. We just identify certain groups of constraints that we know represent functions. Then decisions will be essentially constraints, or adding constraints instead of adding a single literal. And conflicts work a little bit different. We can't use unit propagation only. We actually need a set call to find conflicts instead of just propagating the existing partial assignment and getting a conflicting assignment from y and not y. We have to ask the SAT solver whether there exists an assignment or an input to the functions we have already, such that we propagate y and not y. So that is kind of a major gap between these two worlds. But learning will then be remarkably similar. We'll also learn clauses. And what is, I think, most important, and this is where I think people don't believe me at first when I talk about it, is we need this notion of propagation. SAT solvers would be completely useless without unit propagation, right? So we need this discovery of new things, of unique parts of the solution. And so that is the thing that I think is really novel. If one thing of this work survives a longer time, then it will be this propagation of this property that that certain variables need to have unique Scholen functions. Let's define that roughly, at least. So to define unique Scholen functions, we first need to define what it means that a clause has a direction. We call a clause as a unique consequence. So assume we're given a quantified Boolean formula and a set of variables d that already has a unique Scholen function, whatever that means. Then a clause is said to have a unique consequence, say the unique consequence ln, the last literal here. I mean, we cannot reorder them otherwise. If this variable is not yet in D, it's an existential variable, but it's not in D, and all the other literals in that clause already have either a Scholen function or they are universal. So, in other words, if you want to express it in natural language, this like a clause has a unique consequence L if L is the only existential variable in it that does not yet have a Scholen function. It's sort of like the unit unit clause property, where when all but one literals are assigned, we can propagate the last one. In this case, they are not necessarily assigned, but they just need to have a Scholen function, and then we know that this clause has a direction. Right? Okay. A unique Scholen variable then has a unique Scholen function. If this property holds, we say it must hold that for all possible assignments to the universals and all the unique assignments to the variables in D, right? They all have functions that are so that they're all determined in the universal variables. So for any assignment to X, there's a unique assignment, unique extension to the variables in D. That is determined by the clauses curly D that already that define these Scholen functions, such that there exists exactly one value for this variable V. And if that's the case, then V has a unique Scholen function. And this unique value must be determined only by the clauses with unique consequence, like only those that we have identified to have a certain direction. Then we know that, I mean, this is an approximation of what it means that there's a unique Scholen function. We only take into account these unique consequence clauses, not the other ones, and there could be even whole groups of variables and clauses that only have one unique assignment or something, but we don't find that. So this is an approximation that only takes into account the really local situation, but it's sufficient to find unique Scholen functions in many cases. Furthermore, this can be checked with two simple SAT checks. I mean, as expected, we check whether the relation is locally functional or whether it's locally conflicted. This just means these are the variables. This curly D are the variables. Are the clauses that only contain universal variables and variables in D. So these are our Scholen function definitions, right? Those that we've derived already. And then we ask basically whether the conjunction of all the antecedents of the unique consequences can be satisfied. This means that there exists an assignment for which no unique value for V is determined. You have a question?
You say in the following way. So a clause gives either a lower bound or upper bound for a variable, depending on whether the variable is positive or negative.
Yep.
So Davis will give you the full upper and lower bound, so that this gives you the range of values as a function of other variables. So, and then uniqueness is whether the upper and lower bound are tight, so you subtract the lower bound from the upper bound.
This is a view we'll get to in a couple of slides. Yeah, this is another way how to look at this. Yeah.
And that's where you delay binding whether it's functional.
Yeah, until we find out that it's actually the case. Yeah. True, and conflict will be the same or very similar. We just have to ask whether there are kind of opposing assignments to this. I mean, we don't have to go through these exact formulas. It's sort of clear that we can formulate these small set queries that only go over the neighborhood here, and they also ask the global situation. Now we can approximate these. Oh no, I think I've taken this out of the presentation. But anyways, we can approximate these two checks by just dropping these Golden function definitions. This gives us then the purely local picture, what only happens with the clauses that this particular variable is involved in, and then we get like two different approximations. Like we get an under approximation of what it means that a variable is functional, and an over approximation of what it means that it is conflicted. But we can use that to speed up the algorithm. Anyways, this is just a principled view in it. Now, let's take an abstract view in it again. Let's assume we have some group of variables like before. X's are universal, Y's are existential. D is our set of variables for which we have a unique Golden function. So this is kind of a blue circle. This kind of includes all these arrows, which each stand for subclasses, that uniquely define the functions for y1, 2, and 3. Now, the unique consequences are those that kind of leave that area. We might have a clause like y3 or not y4. Y3 is a variable with a unique Golden function, so we see that this clause must be a unique consequence, or must have a unique consequence. Now, this is a clause that actually should involve, this should be a multi-edge, should include y1, y2, and y4. Sure, and this is a unique consequence because y1 and y2 are already determined. All right, now, exactly, we'll go to this sort of partial function over and under approximation. Each of these clauses with unique consequence define a case of this function definition, right? This clause goes in this top line. It says y4 has to be defined as true if not y1 and not y2 holds. Then the other two clauses define cases in which the variable has to be false. And then we have this unknown area between. Like, there could be more cases we don't really know. The two checks that we do, the functionality and the conflict, essentially to ask whether this question mark area, this middle area, is empty. If so, then it's functional. And we can ask whether there is maybe a conflict, which means that the 0 and the 1 area overlap. Sure. A decision now will be to assign this gray area, the middle area, to either the true side or the false area. We could also take more elaborate decisions, but it turns out that very stupid decisions are often fine. Because if we fail, we learn new clauses and we will get new entries in this function table. All right. Now, let's assume y4 is true, is functional, and it's not conflicted, so we can propagate it. What happens is that, well, we include it in the set D. The algorithm propagates, the D gets extended. These are not unique consequences anymore, but others will be then, and then we can maybe propagate more. All right. I mean, it's pretty straightforward so far. Now, conflict analysis. What happens if something goes wrong and we run into a conflict? When we take some wrong decisions and so on. Let's go sort of back to our previous example. We had our clauses and variables here. We had the conflict for variable y4, which was provoked only if we have this assignment x1 and x2, because then this clause propagates, this clause propagates, this clause propagates. This is nothing else but a conflict graph. No, what's called implication graph, sorry. Implication graph in set solvers, where we have now just two types of decisions. We have universal variables, which are here marked in black, and we have these blue variables, which are existential decision variables, where we just added a clause, right? Because the conflict could only be provoked by, or was only introduced because we added our wrong decision, right? And this wrong decision is represented by these two blue arrows and y3 being true. All right. So what do? We go back in this implication graph, learn a clause, in this case, not y1 or not y3. This is what we learn. Okay, I think I missed that implication step, the animation step here. So, yeah, so we learn a clause, add it, and continue. This gives also rise to the complexity of this algorithm. It's an X-based algorithm, like CDCL, because in the worst case, we have to add all clauses, right? Particularly in the case that all variables occur in all clauses, we get like really big clauses, right? Really a lot of clauses in the end. All right. Cool. So we can actually go already to the evaluation. Now I want to get back to the. Pardon? Like in set solvers, like heuristically delete them, or yeah, you can. I mean, as long as you eventually allow to learn arbitrarily many, yes.
Well, in set solver, you can just do quite a lot. You can stop. You can trade restarts.
Yeah. These are things I won't show here, but yeah, my algorithm does do restarts, and the implementation does do restarts, and I also experimented with deleting clauses, even though that currently doesn't help so much, pretty much because the rate at which it learns clauses is 100 times slower than in set solvers, and so I never collect that many clauses. That's really an issue, though that might change. So it's kind of, yeah. Okay, we're going to take a look at the benchmarks that we've defined earlier, ranking functions, function summaries, and program sketches. Then we'll take a look at the QBF eval evaluation. Unfortunately, I have only the 2016 results, not yet the updated results. I'll talk a bit about that, and then about certification. Now, ranking functions. So evaluating QBF algorithms is a bit hairy, so, but we'll walk through that. We see solid lines and dashed lines. Dashed lines are those that use preprocessing, and solid lines are those that don't use preprocessing. The reason why you don't see many solid lines is that without preprocessing, these algorithms cannot solve basically any of the benchmarks. Right, this is pretty sad. We see that one red line, which is DEP-QBF5, because it kind of uses in-processing, and I couldn't deactivate that, and then it would, so it does, so it uses the pre-processing techniques just like while it's running, and therefore sort of at least solve some of them. If you use the full preprocessor, it can solve basically everything, and this is why all these lines are pretty much the same. But like as soon as the preprocessor stops, the algorithm still cannot solve much on this benchmark. It's a bit hard to see. I think these algorithms can solve all but 2 or 3 of these benchmarks. However, cadet, which is our implementation of incremental determinization, the algorithm I just presented, can solve all of them, and it can typically solve it a factor of 2 to 5 faster or something. Like it's typically in the order of like 20 milliseconds, like maybe sometimes up to 100 here. I think the worst case was a couple of seconds. And these were benchmarks that included 64-bit encodings of small programs. That's kind of reasonable. It's already pretty nice. Of course, here the preprocessor, because it's kind of a standardized or like a preprocessor everyone uses, could use pretty much could solve pretty much everything, and therefore, I mean, it's not maybe not the most interesting benchmark yet. Now this is a different benchmark, the function summaries, where it looks already a bit different. Again, dashed lines represent the solvers with preprocessor, the other ones without. Again, without preprocessing, the algorithms cannot solve anything. With preprocessing, they sort of get somewhere. But the preprocessor was sort of solving things until that point, or that point, I don't exactly know. Now we have some other lines straight through it, and I won't go too much into details here. What we see is that, again, cadet, our implementation is like a factor of, and this time like 10 to 20 times faster on the average instances, and can solve everything here. That's pretty cool. Can even like really solve. These were actually interesting, like the computation of function summaries. So this would be actually a nice verification effort there. For the synthesis benchmarks, we couldn't solve everything. It doesn't quite continue like that. And also the gap was really smaller. I mean, sometimes for some time bounds, other solvers were even better. But it turns out that with like a 600-second timer, we could solve pretty much. I kind of cut off the graph here because there were a lot of really boring instances, and then only, I think, the last like 20 or 40 were really interesting. So we already see like this new solver gets somewhere. Now I want to add here, this comparison is again really like it's hard to compare these algorithms because all the algorithms are not super clean implementations of just one thing, but they kind of try to do some tricks here and there, right? Like as all solvers typically do. So for example, in our cadet implementation, I also implemented that when it sees that it can just enumerate a certain thing and it's reasonably small with some arbitrarily chosen cutoffs, it will do that. I mean, its own interest is to solve a thing. It's not only a clean implementation of the incremental optimization, even though that is the main thing that happens. For most of the instances, it sometimes also does. So I just want to add a word of warning here. It's not 100% clean. Neither of the algorithms are clean implementations of anything, I would say. It's a bit of maybe I'm a bit too harsh here. Anyways. So the QBF eval 2016 looked like that, which is pretty cool. Cadet is pretty strong here. That's a 2 QBF track only. However, for the 2017 benchmark, I hadn't time to generate this graph. There, Cadet only won the second prize because there was another solver that came into the race. They just solved like I think like 4 instances more or something, like really hard. But the other solvers are still kind of far off. This new solver is basically doing reconstructing a circuit representation from the CNF and tries to do CGAR on top of that, and that apparently solves also things. I mean, it's like I'm not exactly aware what this guy is doing. We'll look into that. So there's still, I mean, still some competition going on, I would say, between the two approaches. I don't want to say CGAR is bad, just there seems to be some decent progress happening. Yeah, Will Cleavers, yeah. Yeah, Ghost Tube. Last year it was still pretty far off from the other solvers. It won competitions in some earlier instances, like here you see the yellow line is this one. But apparently he implemented some new circuit detection that is way better than the earlier one and could solve more. I don't know what the exact advantage is, or exact thing that is in which way he improved this thing. I don't know. All right. All right. I think we can see that this new algorithm. So this new algorithm actually helps us to solve more instances, like interesting verification benchmarks. It doesn't rely on enumerating inputs. It's often really fast on like average instances or easy instances. It doesn't require preprocessing, right? Like Cadet never used any kind of preprocessing, which is really important if you want to create a proof over the formula, and so that gives rise to this picture, which is a bit show off, maybe too much. I don't know. Here collected set instances from all these benchmarks and ran the only 2 solvers that are able to certify. Actually, there's a third one that is also due to me and a colleague, but that's pretty much the same as that QBF here. And I measured for the different instances the sizes of the certificates. Now, not only can Cadet solve way more, it can also the certificates are just like many orders of magnitude smaller. I mean, that's not really surprising because there are certificates that look like that. Which is just, this is probably an adder or something, or +1, I don't exactly know, an increment maybe. And all these, I mean, these lower triangles are universal variables, these upper are existential variables, or I think also the nodes are existential variables. And enumerating all the assignments for this thing is just takes way too long. And DepQBF couldn't use many of its optimizations. You have to deactivate many optimizations to be able to certify, and you cannot use preprocessing right now. There are some efforts to re-enable preprocessing and kind of carry through these certificates, but it's still a bit hairy. And it didn't really work for me. And so it's not surprising that DepQBF really, like the number of gates in this really shoots up. It just does a huge case distinction over everything and is really not effective. Cadet, on the other hand, can basically propagate these structures, right? It didn't invent the structure. It was just in the instance and just propagated it. So it's fine. It didn't do much work. It just read the definitions that are in the problem. All right, so, and it spews out these sockets. I mean, you see there are some weird things happening below here and below there. So it probably added some weird clauses there, learned some new clauses, and then it returned that thing. Okay, now, okay, to summarize this first part, okay, we're already pretty much at the end. We have seen that this algorithm, like we have seen this definition of propagation, in particular of unique consequences and unique scaling functions, the partial function view, how conflict analysis works roughly, and why it's terminating, because I mentioned enumerates all the clauses, and we have seen the exponential relation. What we have not seen is all the details, like how it's exactly implemented. It's pretty close to a SAT solver when you sit down implementing it. It's really not that much of a difference, just that you need to have like this extra SAT solver inside that kind of generates a conflict and so on. And there's other notions that really help to speed things up, like pure literals, restarts, speed heuristics, and so on. So these are all implemented in the solver. Okay, now I want to, in the last couple of minutes, I want to at least add one new note, one interesting note. This algorithm can, I think that one view in the algorithm is that it can really symbolically compute functions, scaling functions only for 2QBF right now. And the question is whether we could maybe extend it to compute not only scaling functions, but general functions. The difference is that for 2QBF, scaling functions all have the same domain. Right? And we might want to introduce functions that have different domains. We might want to actually work with a logic that can introduce extensionally quantified variables, functions that have different domains. And then we have a sort of QBF here that can use the function applications inside. There is a logic called dQBF that can pretty much do that. It's also similar to EPR if you do some encoding tricks. So that would be super interesting. And I think in particular for verification purposes, it would be amazing to have a symbolic algorithm with that really can treat these functions in a symbolic way, because we can represent the whole memory state or the whole state of a system by that, by a function. We can even represent the whole execution symbolically. Which is just here, this is mapping addresses to bytes, right? It's simple. And we can represent data structures, arrays, strings, maps, and so on with functions. So functions are a really natural way how to formulate problems, how to think about it. Also, we humans would never enumerate the inputs of a function. We would kind of think about them symbolically. Also, our proof objects like ranks and ranking functions or invariants are, naturally expressed as functions. Now, many of these things I've been talking about are currently addressed by specialized algorithms, for example, in SMT solvers and also elsewhere, like theories like EUF, arrays, and so on. However, often they tend to represent these functions as function tables, by which I mean that they sort of introduce one variable for every possible input, at least for the inputs they need to consider. And so they kind of expand it into a more flat problem and solve it there. That is surprisingly effective. There has been a lot of work. It's pretty good. But I think we could maybe, come up with a symbolic algorithm that at least helps in the cases where these other algorithms explode. Now, the question, of course, is how could we possibly argue symbolically about these functions? And I'm not aware really of algorithms, maybe in the first order theorem proving world, but also there, I'm not so sure. I'm happy to hear about your opinions on that, but yeah, you seem to have a...
Check with Christoph Weidenbach.
Yeah, I try to, but so far he hasn't convinced me.
Function or what he's...
Yeah, okay. Oh, yes. Okay. Okay, cool. I'll try to get more out of him. Anyways, let me present what I think this could go. And for that, I've been looking at or investigating how we could possibly reason about these functions. And there's one major problem, and that is that resolution does not seem to work, or it doesn't seem to cut it for dQBF. So a CDCL solver for dQBF is just not possible, because CDCL just does strictly resolution in the end. Now, for SAT and QBF, resolution just you can solve setting QBF by resolution by just building all resolvents in principle, and if you derive the empty clause or a clause that only contains universals, you're done. For DQBF, there exists an example due to Balabano et al. That shows that this is not possible for DQBF. Now, presume we have this logic that allows these function applications in clauses, just treat them as atoms for now, and then there exists this formula, which is introduces this one function that maps like bits to bits, single bits to single bits, and then the formula just says like whenever x1 and x2 are true, then f of x1 should be the same as f of x2. I mean, the one direction is easy to define, but the other direction is actually doesn't seem to be easy. I mean, it's like it's clear that such a function cannot exist. There are just too many assignments for which these are. I mean, there are 3 assignments of 2x1 and x2 where they are not the same, but f of x1 and f of x2 cannot be consistently defined to satisfy the equality. And you can try it out in your head. It's really just a small combinational problem. And it turns out that even if you now try to build more resolvents for this sea of clauses, all the resolvents are either trivially true or they are already contained in this set of clauses. So you cannot derive a new clause, but the formula is false. So resolution doesn't cut it here. Now, and all the complete algorithms of DQBF so far essentially also in the end up to resolve that only by expanding the function tables. Yeah.
For this, you have to do a universal reduction. You have to replace in the first clause you replace x1 by 0.
You could try to insert like concrete values, yeah, but then you end up enumerating values, yeah.
No, the preprocess the call you. So why do you claim that resolution cannot derive a new clause?
You literally cannot derive a new clause through resolution in this thing. I mean, you just take, say, the first two.
So I'm telling you that your clauses are not the right format. So you have universal quantifiers on each clause, right? So distributes over conjunction.
But they are, I mean, they're universal quantifiers that are there globally, right? I mean, I know like for first of the theorem provers, they kind of try to keep quantification locally,
yes.
And you try to unify clauses and so on. You can do that. That algorithm works, yeah. However, in practical evaluations, it seems that these solvers are absolutely not even competitive with enumerating things. In the QBF competitions, we had a submission from an EPR solver that converted QBF to EPR and couldn't solve basically anything.
Too many arguments.
Yeah, right. Because the encodings that we are interested in have 10,000, 50,000 clauses. This is not really the realm of these.
Anyway,
But
I'm gonna.
I mean, I agree that there is. I don't want to dismiss their work.
I think this is, but I think your claims are not correct.
Oh, really? I mean, resolution. No, I mean, this is literally a proof, but in their work, and it's really. I mean, and also I checked it myself to really go through this thing. You can take any two clauses, build their resolvent, and it's either trivially true, that means contains like opposing literals, or it is already contained in that thing. I mean, the first two ones, for example, if you resolve them with a pivot f of x1, is trivially true because then you have f of x2 and not f of x2.
So if you, okay, I'm not gonna.
I mean, there are techniques to solve that, but not through resolution alone. I mean,
But yeah, so you're saying you can't solve this problem just treating f of x1 and f of x2 as atoms.
yeah.
As
Yeah,
propositional
exactly, yeah.
atoms.
That's propositional atoms, but it's not the.
Yeah, if you want to replace them then and instantiate them, yes, you can. Then you can solve it. But then you are in the realm of enumerating values.
No.
Okay,
I'll go
cool.
over it.
I'll be happy to
I'll
hear.
show you.
Cool. Yeah, I would be very interested in that actually. Yes. So we kind of then from that point on took a different route than instantiation definitely. We introduced a simple proof system for DQBF that avoids that. I mean, like, I know we are kind of short on time, so I'm going to make this fast. For that, to talk about this briefly, we have to introduce the actual notation of DQBF, which doesn't usually come with functions. Typically, it's formulated in terms of Hankin quantifiers, which look like that. We say there exists a function f that has these inputs, where these are always universal variables. and then you can use that f which is actually sort of a functional application of f to these arguments inside that formula. Now, this is sort of just a normal function where every function just has one set of inputs. And actually, it turns out, we proved in the paper that we can just rewrite that in a linear, with a linear blowup. So we can rewrite this quantification of a function with a linear blowup into that Hankin quantifier representation. Pretty easy. So we now just have formulas like that. We say, like, okay, we have some symbol y1 that depends on the inputs x1. We have some symbol x2 that depends on x2. And let's just zoom into one class, x1 or x2. The question that is really important to ask here, or that really helped me to understand this, is who's responsible for satisfying that class? If we are in SAT, that is, if x1 and x2 are empty, so they're both propositional variables, one of them statically satisfies the class, has to, I mean, for any solution. It's clear. Otherwise, it would be violated. For QBF, we know that either x1 includes x2 or x2 includes x1, probably because x2 is occurs behind x1 in the quantifier prefix. It includes maybe more universal variables, not the other way around. Then we can say whenever the class is not satisfied by y1, y2 has to satisfy it, and it can know because it knows more universal variables. Right? Yeah. Anyways, now we can in DQBF we don't have that property. These could be incomparable. Could have x1, x2 could be just like neither one includes the one nor not the other way around. Okay, in this case, the basic insight was that y1 and y2 have to coordinate based on their shared information. So only on the values, based only on the values of that occur both in x1 and x2, it has to be clear which side satisfies the clause. And this gives rise to our proof rule, which essentially says, given a clause with two parts, just two separate parts, that where the one part cannot depend on the dependencies of the other part and the other way around, so they have incomparable dependencies, then we can introduce a fresh variable, t, that just depends on the intersection of the two dependencies, and this variable t controls which side of the clause has to satisfy the original clause. So we introduce a new function that resolves this thing. We call these classes information forks. It's kind of there's a similar term in LTL synthesis of distributed systems, because it's sort of the same effect here. Then we just need the two standard rules for proving QBF formulas: resolution and universal reduction. Universal reduction just says if we have a class full of universals, we can drop them all and create the empty class. Now, in an example, I can look this. This is just the previous example with the with our functions. Just that now the functions are called. I mean, with this equality of the functions, if and only if x1 and x2 holds. Just that now the f1 and f2 are unfortunately called y1 and y2. So what we just do is we split all the classes because they all have this property that they have y1 and y2. And we introduce these variables t1 to t6, which are introduced positively here, negatively here. They all have empty dependencies because the intersection of the set of x1 and x2 are empty. Then we just apply resolution. We get a formula only over the variables t. We apply more resolution and get the empty clause and are done. We have proven it to be false. So this works, and we have a proof that it makes resolution complete. I mean, these three rules form a complete proof system for DQBF, and we can solve, in a very symbolic way, I would say, formulas that really quantify our functions. It's pretty cool. So far, no implementation exists, so it's really hard to say whether that is going somewhere. By hand, we were able to solve some formulas by that are sort of interesting, but of course, that is so far just an exercise. It's really I don't want to claim I know how to create an efficient solver around that, but there is a sort of connection to incremental optimization that I believe is there, and I'm still working on that. Anyways, okay, now, okay, I don't want to go into the last part because now time is running out. Anyways, a very interesting thing, the quantitative synthesis part. We can approximate synthesis queries with stat solvers, and it's a really cool thing, but I'll leave that out and we're going to jump to the end. Okay, I've presented the incremental determinization algorithm for 2QBF. I've sort of sketched out how this could be maybe lifted to quantifying over general functions, Boolean functions, of course. And there's more work in this area that I would also be happy to talk about. If you're interested, I'm here all day and happy to take questions and discuss later.
Can you just say what quantitative synthesis solves?
Okay.
What's the problem?
The very short summary is okay. We solve that problem. You're given some function from exponential space of natural numbers to another exponential space of natural numbers, where the function can be sharply hard to compute for a single input. We have exponentially many inputs. For each input is sharply hard. We have no convexity assumption, no assumptions at all about this function, not even that it has any informative derivatives or anything. And I still claim we can find an input that is probably close to the maximum, and that with only polynomially many calls to a set solver. That is the short answer. It's through through model counting, and there's a very neat trick how we can extend that to actually turn it into an optimization algorithm. Yeah. Yeah.
So I think
Thank you.
let's thank Marcus for his presentation.
Yeah.